Perfect. Okay, so this is going to be kind of a high-level overview of zero-knowledge proofs. So let me get you guys on top of the screen here, so I can see you. Okay, great. Okay, let me know if anyone cannot see this, and or if anyone has issues during the presentation. We can go through and troubleshoot. But okay, so I'm going to start out by talking a little bit about zero-knowledge at a high level. Okay, this is the QR code for the talk. I sent you guys the link in the chat. Okay. So just as a starting point, I think the reason I got into zero-knowledge cryptography is because I think this is the most important technology that no one is talking about. So fundamentally, zero-knowledge cryptography lets you prove a fact without revealing why it's true. So it's built out of several other cryptographic primitives, but at a high level, it seems kind of magical, right? So it's like the equivalent of playing poker. You claim to your opponent to have 5 of a kind, and the only way for you to prove that to your opponent is by showing them the actual cards, by revealing the fact that you had 5 of a kind, right? And then they see it and they're like, okay, you win or whatever. In this case, you basically be able to prove you had 5 of a kind without actually revealing, in like the suite or which kind, what card it was or anything like that. So it's a totally new paradigm that has a ton of application in both Web 2 and Web 3. It's kind of similar to AI in a little bit in many ways. AI machine learning kind of was developed in the 60s, 70s or initially, and then kind of went through a long path to becoming practical. I think zero knowledge is much the same. I mean, in the 80s, it was invented, but it was just extremely impractical. And only in 2010, basically, did you have the first real practical zero knowledge systems. And then, with cryptocurrency and blockchain technology, there became a lot of, it became of interest to folks because, it helps you, preserve privacy in these systems. So since blockchains, since Zcash in 2016, you had this massive Cambrian explosion of different proof systems with different capabilities. And we'll kind of get into some of that a little bit later. Okay, short history. This is just, yeah. Okay, so this is like the dad joke. I am a father of 3, so I like dad jokes. Apologize. Okay, so the idea, it's a joke of 2 cryptographers walk into a bar and that's kind of the joke, but it is actually, it's not entirely untrue of how, or it's not entirely off from how zero knowledge cryptography was invented. It started from this concept of interactive proofs, right? So it was a concept that theoreticians discussed, where it's like, okay, imagine you wanted to it was very practically motivated. You have mathematicians or theoreticians in computer science who are reading papers and they're reading proofs and they're like, man, it's very, very time consuming to go through line by line by line all of these proofs. And then, we have to make sure we go, there's really no shortcut to knowing whether or not, this theorem is correct unless we read this line by line. So people started wondering and kind of thinking about a problem where what if you had some kind of, if you were trying to convince someone of the truth of a theorem, is there any way to do that other than walking them through everything step by step by step? And so this is kind of the idea of interactive proof systems, right? So in this model, you have a prover and a verifier. Prover says, hey, I have some results. And then there's some communication. And at the end, the verifier either accepts or rejects. These are interactive proofs. Now, the interesting thing is, it's a really fascinating area, complexity theory, but we're not going to get too much into it. But the takeaway from this is that actually, for a huge range of problems, it is possible to verify their correctness in polynomial time, even if the problem to compute takes more, NP. So it's anything more than polynomial time, effectively. And so it's got a huge range of applications. Okay, so again, this is basically the idea. It's like Alice makes a claim, Bob asks some questions, Alice answers, and then Bob accepts or rejects. And again, the key thing here is that the time measured in the transcript of the interaction is smaller than the computation. Okay, so you can, so these are the properties that you need is completeness, which is to say that Alice can prove any true statement is possible to prove to Bob, and soundness is that Bob should not accept a proof that is false with 100%, with 100%, or sorry, with a statistically extremely small percent, probability, right? This is how a lot of cryptographic proofs are done, where it's basically the possibility of someone guessing, the preimage to a hash function, for example, is just vanishingly low. Similar idea here. And then zero. So, okay. So anyway, so people were playing with these things. And then in 1980, there were some researchers at MIT actually who invented this. They basically said, hey, could we make it so that the verifier learns nothing about the computation being run, except for the fact that it's true, right? Or except for the fact that it returns true. And so this is basically the idea, right? So this is the paper that really arguably kicked off zero knowledge proofs. Okay, so
just a funny, historical fact. I think literally Charlie was saying that it took them about like 3 or 4 years to publish that paper. It was getting rejected left and right from all the conferences.
Yeah, actually, I'm Dan. So I used to, I was at Stanford and I studied under Dan. And Dan was very fond of saying, he's like, you're on the right track if your paper is getting rejected, right? Because I think also like Ralph Merkle. I think Ralph Merkle initially, when he proposed like the concept of a Merkle tree, I think it got rejected a couple times, and then of course now it's anyway, yeah. So if any of you are academics and your paper gets rejected, that might just be the first step to greatness. Anyway, okay, so now that's kind of like, that was step one to zero knowledge proof. So if you do what's outlined in that paper, you have an interactive proof system and you kind of sprinkle on the zero knowledge, you get Sigma protocols. So these are what are called Sigma protocols. So these are an interactive protocol in which the verifier learns nothing. So there's the zero knowledge property is maintained. And then you take a Sigma protocol and you do what's called the Fiat-Shamir transform, which basically is you simulate the questions that the verifier will ask based on the output of a hash function, right? So you can like use a collision resistant cryptographic hash function, like get an output, and then you use that basically to like mask the potential questions that the verifier would ask. So you can kind of simulate what the verifier would say in a way that can't be biased by the prover, because of course, like it's a hash function. So that's what gets you NISICs. These are non-interactive, zero knowledge. So non-interactive, it's usually just called NISICs, but it's non-interactive zero knowledge proofs typically is what you say. And then if you take NISICs and you do some magic things, and we're not going to get into that for the purposes of this, but polynomial commitments basically is like one of the really key magic ingredients. You get ZK snarks, and the key factor and the key piece of ZK snarks is that in fact, I think it's on this slide, zero knowledge, succinct, non-interactive argument of knowledge. And so the succinct part is really, really important here, so that in this case, like the proof is very, very small. And in fact, it's independent. The proof size is independent of the statement being proven. So that's really obviously a really big deal. You can prove a very, very, very large statement, but the proof size remains the same. So that was a big step forward. And really, this is arguably what enabled these applications in blockchains. One quick note here, I'll pause and see there's lots of flavors of zero knowledge proofs. And I think like it can be confusing around like what is a Stark versus a Snark. So Starks stand for succinct, scalable, transparent argument of knowledge. They're actually a subset, technically. It's a subset of Snarks that uses some different assumptions and some different cryptographic primitives under the hood. And we're not going to get, there's like a lot of great stuff written on like, what are the advantages of a Stark-based construction versus what are the advantages of like a traditional Snark-based construction. Really, it comes down to the polynomial, the commitment scheme being used under the hood, but there's a lot online about that. I don't want to bog us down here. Okay. Yeah, cool. So this is basically just kind of showing the progression of how we got to Snarks from Sigma protocols to Snarks over the last 30 years here. And you can basically, like the point of as you can see, we've kind of been on a linear progression. Things have slowly but surely gotten better and better and better. Groth 16 was, of course, actually, I think Pinocchio was actually the first Snark that was used in Zcash. I don't think it was ever deployed to mainnet, but it was the first one they started with. And then Groth 16, if you hear Groth 16, that's a reference to a paper written in 2016 by Jens Groth. And it was a construction that for polynomial commitments mostly, where people applied to ZK proofs, and then that really was what enabled. That was the Snark that was deployed with Zcash in Seedling or Sapling, maybe. No, not Sapling. Anyway, it was one of the early ones deployed in Zcash, and then from there, you guys have probably heard of all these other things, right? You have Starks, you have Plonk, Marlin, which is the proof system that Aleo uses, Halo 2, and these things have just gone from being, relatively limited, relatively slow, to being like pretty flexible and actually pretty performant. We'll talk about that more. Okay, we talked about this already at the beginning. This is why, basically why I think this is a game-changing technology, is it lets you prove something without revealing why it's true. Typically, there was always this trade-off, like, what information do I reveal to prove the veracity of a statement versus what do I want to keep hidden to make sure I, like, for whatever reason, I don't want to show this information. And you can imagine a million areas that this applies. Like, one obvious one is medical records, right? So it's like, I want to prove that, I meet, I'm a generally healthy individual to an insurance company or something without revealing like all of my medical data, right? So this is an example of how you do that. Now, there's other cryptographic primitives. If anyone has questions later, there's other approaches in cryptography to doing that same thing. And if anyone's curious about those, we can discuss those again. So, yep. So this is what I like to say: they conceal and compress information, right? The concealment comes from the zero knowledge property of the ZK snarks, and the compression comes from the succinctness, right? So this is actually, for many of you who may or may not know, but in ZK rollups on Ethereum, typically the zero knowledge property of ZK snarks is not used, right? So you don't care about it, right? The point of the ZK rollup is to have a verifiable computation about these state transitions, and that are batched and compressed down into a single proof. So you have the S in the snark is really another key piece that enables scalability of blockchains. And this is exactly what they're used for in rollups, not actually privacy, because with a rollup, you have to publish all the data on chain anyway. So the zero knowledge property really doesn't matter there, but the compression property is very important. Yep.
And Alex, I guess on that, right? I guess like most of the hardness, right, or complexity in a lot of the systems actually achieving the proof part of it, right, or the compression part of it, and the concealing part comes kind of as an add-on on top. That's a little bit easier to orchestrate. Is that still the case with latest constructions, or kind of how do you view it?
You kind of get, well, yeah. So it's difficult to separate them, because really both properties. So there's really two parts of any ZK proof, like or any ZK snark. You have the interactive Oracle protocol, which is like basically the transcript and how like the verifier is convinced of a statement. There's this whole that's sort of like the interactive proof part, and then there's the polynomial commitment part, or the commitment part, right? Because the idea is that the prover has to commit to like the answers to the verifier's simulated questions, or rather has to commit to the transcript of questions that the verifier is going to ask them before they run the computation, right? And so this is really the key piece where the compression comes in, because the thing about polynomial commitments over elliptic curves is it basically lets you compress all of the information in an arbitrarily sized polynomial into a single elliptic curve point, or a handful of elliptic curve points, depending on the construction. So that it's just like a hash function, like SHA-256, for example, conceals and compresses information. If I hash my name, like my however many bits of Alexander Pruden, like that goes to 256 bits. So it's compressed the information. And then of course it's concealed the preimage, right? So that it really, both of those properties are in the commitment schemes. And this is why most of the work around iterating on these different constructions is there in the commitment scheme. Does that answer your question, Sergey? I don't know if I just confused everybody more, but is that helpful?
Yep, makes sense.
Great. Yep. Okay. Here's use cases. I'm going to run through these kind of quick, and then we're going to jump into Aleo. Regulated stablecoins. I mean, I think USDC, but like cash. So, Sergey can't just look at my my Ethereum address and see who I've paid for my all time. But you can have a regulator that says, hey, like just like USDC works today, where Circle maintains a blacklist that matches the OFAC sanctions list, and then you cannot transact in the system, but by the smart contract unless you are not, unless you're complying with that blacklist, right? So you can imagine whitelist, blacklist. So you could construct these various regulated stablecoins, which actually was a use case in the Zexi paper, which we're going to talk about because the Aleo is based on it. But yeah, so this is one good use case. Dark pools. Another one is exchanges or on-chain OTC. So for any of you guys who are familiar with markets, you have a variety of different venues to trade assets. You have, like, for example, a stock exchange like NYSE, it's a traditional exchange. But there's downsides to that, and particularly in crypto, where everybody can see your trading, or see your intention before you execute a trade. This is kind of what MEV is. But in this model, theoretically, you could do it something like a dark pool, where you could trade larger amounts, hide the identity of the counterparties, and kind of simulate what you have in like OTC markets in finance. Proof of solvency. So this is a use case that actually some research came out of Stanford about. So this is like the idea of, you're Celsius or something like that, and you want to prove that your book is not just full of bad loans. You could theoretically prove it without revealing what your loans are. Passwordless authentication. Identity is actually a really big one that I think is going to be really important for Web3, like the ability to authenticate to a protocol or something without necessarily revealing everything about you, right? Again, today, to do that on Ethereum, for example, you need to associate your real world identity with a wallet address. And then that wallet address, of course, everything there is fully transparent. So, for example, I have an ENS name. Anyone could go to my, my ENS name resolves to an Ethereum address. And then so if I have a credential, for example, like I have to share not only that credential, but everything every time I authenticate. And so zero knowledge cryptography potentially lets you do this in a little bit more fine grained way. And if anyone is familiar with the proposals that actually date back 20 years now with the W3C on how to do digital identity, it's quite obvious that something like zero knowledge cryptography will be required. Okay, let's skip a lot of these other ones. Maybe the only one to point out is Mina. By the way, this is like the Mina use case. Mina also doesn't use the zero knowledge property of zero knowledge proofs, but they use the compression property, and they use it in a really interesting and clever way to compress down the entire state of the blockchain into a single block. By the way, since I'm talking to Axelar, this is actually the property that a lot of people are looking at. It's like the same approach to what a lot of people are looking at for bridges, right? For ZK bridges. And maybe Sergey, you guys can, you probably know better than me on the current state of ZK bridges, but fundamentally the idea is that you can make a super light client that can cryptographically verify, the state of a chain by only having like a single block, right? Or, the state of an entire blockchain can be represented by a single block, and that can make for as a primitive you can use for bridging. Privacy preserving machine learning. This is one that we're just starting to explore. I think there's a lot of really interesting ML use cases for ZK. So, I mean, it's just two obvious ones. It's like you want to train a model on some data, but you don't want to reveal what the data is, right? Or you want to run a model that's already been trained, and you want to, you prove a certain output given data that you also don't want to reveal. So you have to prove the model was trained correctly, or prove that the model produced a result without revealing the data that produced it. Gaming, I really am excited about gaming. Dark Forest, I guess I'm not going to linger here, but I'll say if you guys haven't checked out Dark Forest on Ethereum, definitely check. Actually, I think it's on Gnosis chain now, but it's a really cool game that's powered by Zero Knowledge Crypto. Also came out of MIT. Sergey, do you know those guys? Do you know Brian, by the way?
No, I don't.
Okay. Anyway, really cool. Highly recommend checking out. It's a lot of fun, and it's a cool, kind of showcase of what you can do with zero knowledge in a gaming paradigm. Okay, cool. Challenges. Okay, biggest challenges with ZK in the context of Web3 is it's generally incompatible with the EVM, right? And why is that? Okay, so the EVM is a virtual machine. It's run in a distributed network of computers, and the virtual machine kind of operates over 256-bit words. And the problem is ZKPs are, what are they fundamentally, like, you boil it down. In fact, actually, I'm just going to go, let me go to, this is actually a good segue to my other deck. So I'm just going to jump right into the Aleo deck right now. And so give me 1 second, pull that up. This is actually a perfect segue. Yeah, okay, cool, perfect. This is the one that I want to talk about, I want to bring up. Okay, great. Share my screen again. Okay, hopefully everyone can see this. Okay, so now we're going to talk a little bit about Aleo, and we're going to talk about the challenges of, actually, I'm just going to jump there because that's where we left off. So, okay, ooh, you can't see this that well. There we go, hopefully that's better. Okay, so why is it hard to do on Ethereum? Well, again, Ethereum is a virtual machine that operates over 256-bit words, and crypto. And this is right here on this slide is what a zero knowledge proof is. It's a polynomial that you're committing to over a specific elliptic curve, and the finite, and the scalars are finite field elements. So bottom line is, like, if you didn't understand any of that, the takeaway is that, like, it's apples and oranges. Like, these are basically talking about two different domains. And so it's very, very expensive to convert between those, right? And this is why ZK EVMs are very, very hard. Is fundamentally what it comes down to, is you have these proofs which are fundamentally cryptographic objects. And actually, this is the slide that I have here, right? So it's like, you have to both evaluate the program as you normally would. So just like, a normal computer would, but then you also have to generate the proof, which of course you do on the computer as well. But like fundamentally the computer, is representing the proof object as a different mathematical form. I'll probably just leave it there. But that's one of the big challenges of zero knowledge proofs. And by the way, this is what motivates Aleo. This is, I guess I'll transition to Aleo here. So Aleo is building a general purpose smart contract blockchain that leverages both properties of zero knowledge, that uses zero knowledge proofs all the way down the stack. And it leverages both the zero knowledge property to conceal information, as well as the succinctness property to compress it and make things scalable. And the reason why we're not a roll-up is because it's much, much, much more efficient to build everything from the ground up in this model, from the virtual machine to the intermediate representation of the language, all the way on up. You can get much, much better performance. And I would argue it's the only way to do this practically today and probably for the next few years, despite what all the marketing hype of ZK EVMs is. Personal opinion.
Alex?
Yes.
I guess a question here. There is the proof and the VM part of it, right? And I guess I'm curious, how portable is that, to be able to instantiate like in other types of chains, consensus mechanisms that apply in like other scenarios, or it's sort of attached somehow to your chain and inherent to it in one way or another?
Yeah, so Aleo is itself an instantiation or an implementation of this protocol called Zexy, which I'm going to publish in here, let me find my chat. Okay, that is the paper. Howard Wu, who's the founder and CTO of Aleo, was a co-author. And in Zexy only describes the VM effectively. And so in the Zexy model, like, you can theoretically just take the VM and put it on any blockchain, or it doesn't even have to be on top of the blockchain. The blockchain is really there to do two things. One, to just come to consensus about, that a given proof is in fact correct. So you basically have a network of verifiers that just come to consensus about, yes, this proof is valid, right? And that's just, so you go through the cryptographic process of verifying a proof, and they come to consensus, and then that affects a state update. And what is a state update? What is the state being stored there? The state is a tree or a trie of records that have not been consumed, and then a trie of serial numbers of these consumed records. So if you're familiar with Zcash, it's the exact same model. So Zcash has two tries of state, right? It's the unconsumed UTXOs, and then the ones that have been consumed. You basically you need to maintain both to make sure that people can't double spend. But that could really be in Zexy, that like could be a blockchain, that could be a server. It doesn't actually specify that any particular consensus algorithm or approach there. Does that answer your question, Sergey? Well, actually, let me tell you about Aleo, because maybe that was the actual second part of your question. So in Aleo, because in our case, it's a little more complicated. It's if you wanted to take just Snark VM, for example, which is the VM of like our implementation of Zexy, and just put that on another blockchain, it's not totally trivial, because the way we've architected it, Snark VM has all the cryptographic logic. And again, because the Snark OS has to verify cryptographic proofs, Snark OS is the blockchain part. It has to verify cryptographic proofs that, it does call into Snark VM. So TLDR, like, it's a little bit more complicated than just taking Snark VM, which is our ZK VM, and putting it on another chain. You'd have to do a little bit more work than that in this case, but in the abstract model of Zexy, it doesn't matter. Is that helpful?
Got it. No, that makes sense. And I guess just another related question. So you mentioned that you have like consensus to agree like on the on the proof right at the end or something like that.
Yep.
But like, why do you need that, right? With zero knowledge, right? Like I can generate a proof, and assuming you have some type of like data availability sort of chain,
Yep.
right, where anybody can fetch the data. Proof is self authenticatable with respect to that data, right? So why do you need something
Yeah.
like a consensus?
You don't necessarily, I don't think it depends on the use case, right? I mean, I think in this case, like we're talking about UTX, basically we're talking about money, right? So it's like the proof, verifying a proof is, is effectively consuming a UTX, you're effectively consuming a UTXO and creating a new one, right? So Aleo, the way to think about Aleo and generally Zexy is it's kind of in the UTXO model. So if you're, if you're doing like Zcash, for example, like why do you need to come to consensus about proofs in Zcash? It's the same model. I mean, by the way, in case I didn't mention this, all of the authors of Zexy were Zcash founders, except for Howard. So you don't need it, but the thing is, like, the verifying of the proof is the equivalent of, in Ethereum, you actually running the transaction. So, the VM actually runs the transaction. So every node every node is supposed to, when they get, when a new block is processed, you're actually supposed to run all of the transactions in that block and make sure that they did, in fact, come to the same conclusion. And then that's what the network comes to consensus about effectively, right? So the verification is that on the network. So it serves that purpose. So if you didn't verify a proof, or if I just verified it, if one node verified it, like, how would they update the state for the whole network? Like, basically every node in the network has to verify, and then they update the state, and the state is in these two tries. Does that make sense?
Makes sense. I guess
it's related to, like, that's like the prerequisite to updating the state. If you don't come to consensus about that, then how would you update the state? So even if you had the data, like, so if you didn't care about an application where, like, you had effectively these on-chain assets, right? Or if you didn't have an application where you cared about state that you were coming to consensus about, and you just wanted to have like a repository, like a data availability repository, then yeah, you don't necessarily need consensus for this.
Makes sense. So
I'm not sure if I'm answering your question, but if I'm not, then if you could give me like a more concrete, like, what do you think? Like, I understand what you're saying with like the data availability, but I think the question is really like, what are you doing with the data, right? If it's something that, if there's state, that it really comes down to, like, what do you need to come to consensus about some kind of state, right?
Yeah. So I guess just put it another way, because you're not running, a proof on an entire state transition machine of the whole chain, right? There's no single proof. And so you have like individual applications generating their proof, but you still need to have like global settlement between them and sequencing between them. And so you need consensus for that.
Exactly. Okay. That's fundamentally it. Yep. But this is an important point to note, actually. So one of the cool things about this model is that you have, in fact, let me just, actually, before I get that, I don't want to like lose time to not get through the slide, but there is one cool thing I want to mention about this model that's different from Ethereum, and I'll get to it at the end. Okay. Okay. So we've talked a little bit about Aleo, but what is it? Okay. Yep. Decentralized layer. So it's basically a new ZKVM building our own layer 1. And why are we building our own layer 1? Well, because it's much more efficient to do it this way. Okay. This is what the stack effectively looks like. We have the blockchain, which we call Snark OS. We have Snark VM, which is our implementation of Zexy. We have Leo, which also contains, Leo is the high level language we've written. We also have written an intermediate representation for the Leo language, which is halfway between the high level syntax of Leo and R1CS, which is like the building blocks of zero knowledge proofs. And this is kind of our IR. So if you could, you kind of think of it like Leo is like Rust, and AVM instructions are LLVM, basically. So for those of you who are familiar with programming languages. Yep. Okay, cool. So I think talking about programming languages, yep. So this is kind of the idea, is like, you're trying to express a high level idea in math. And so actually, I gave this talk to a bunch of people from the Ethereum world. So if you guys are familiar, there actually is this concept they have this IR for Ethereum called Yule. So you can theoretically compile Solidity to this IR of Yule, and it potentially, or you can even write code in Yule directly, and potentially it's more efficient and safer. Okay, I'm gonna skip all this. We talked about what zero knowledge proofs are. We're gonna skip this. And yeah, okay, so this is how Leo and the AVM works. So you write Leo code. Let's see, I think I have some Leo code right here. Yep. So, and by the way, if anyone's interested to check out Leo, I will put the link in the chat. It is, everyone can go to leolang.org, and then you can go kind of see and play around with Leo and get a sense of what it looks like. Yep. So, okay. Yep. So we have a formally verified compiler that we're working on. So why is that important? Well, if you're writing a program and your compiler produces a bug, and now you're generating zero knowledge proofs that are hiding all the information about the output to a third party, you potentially have a problem. And so it was important to us to have a compiler that we had formally verified. One of the this is actually, some of you may remember Zcash. There was an inflation bug, and they patched it, but it's still an open question of whether or not it was exploited, right? Because of course, because every transaction in Zcash is a zero knowledge proof, you actually have no idea whether or not the bug was exploited. It's an interesting kind of philosophical question about zero knowledge, where you get the benefit of being able to conceal information, but in some cases, it's helpful to know, for example, when something was exploited. And in this case, it actually makes that much harder. Okay, talked about the AVM. So the AVM is, what we call the AVM, is kind of what we consider to be the intermediate representation. That so you write Leo, it compiles down to AVM opcodes, and then that gets turned into R1CS. Okay, so DPC stands for decentralized private computation. This was like a primitive that was mentioned or invented really in the Zexy paper. And so this is what it looks like, end to end for us at Aleo. So we have Leo, you write your program, you compile it into the IR, which is AVM instructions. And then you have I put provider here. This provider should actually be prover. So the prover can then take these AVM instructions, synthesize the R1CS from those, and then taking the parameters from the trusted setup ceremony, which we can talk about if anyone has questions. From that, they can generate a zero knowledge proof and create a transaction, which they, using Snark VM, and then that gets submitted to the network, which is Snark OS, and then state, the network nodes verify the proof and then update state. The proof, again, I guess the one thing to note is that the prover could be you, or you could outsource that to a third party if you wanted to. Cool. Yeah, and I guess like in the future, this is kind of a slide talking about the future. Like we would like it someday to support multiple different languages that compile down to the AVM. So our goal for the, Leo is kind of the way we want developers to kind of onboard onto ZK programming in generally, but the long-term goal is to really focus on AVM and making that like the LLVM equivalent of ZK computing. Okay, cool. This is way out of date. I think this is actually like Nor actually has most of these features now. And so this one's a little bit, this is
Alex,
yes.
sorry to interrupt you here. I just have a question regarding programming languages. I have experience in past writing a compiler, let's say in this application will be to transpile JavaScript into Leo language. Will it be possible? Is there anything like too specific about Leo language, or it's like really high level?
That is beyond. So I'm not sure if it's. Actually, I don't know. That's a good question. Actually, I should ask the Leo guys, and I'll get back to you on that. I don't think there's anything terribly specific about it. It's really the IR where like that, writing JavaScript to target the IR would be hard, but I think you should be able to transpile JavaScript to Leo, for example. Now, how efficient that is, I'm not sure. But it's a question. I'll ask the Leo guys, and I'll send you an email, or I'll put it in the Telegram. Good question, though.
Yeah, that's good. Because yeah, go ahead. Sorry. I just want to say, in JavaScript world, it's a standard practice compiling TypeScript to JavaScript. So in the same matter, like TypeScript and JavaScript both could be compiled into Leo.
Yeah. I'll get back to you guys on that. It's a good question. Okay.
But I guess on that, right? Like, isn't like one of the things that like you have to unroll like all of the computations, right, to be able to perform those, polynomial operations. So if you would,
yeah. Well, okay. So there's the nice thing about the IR is that it basically unrolls all loops and fixes the size of the arrays for you, right? So in the IR level, yes, at least the way we've architected it. So Leo, you can theoretically write an unbounded loop. So I guess maybe this is an important point to note, like what is the limitation of this paradigm, zero knowledge in general? Can you have a VM that is Turing complete? The answer is no. Why is it no? Because let's go back to this slide here. Like you have to represent every program as a circuit, right? And basically what you have to do in advance is lay out the circuit. And then you have to like, then you run the proof that you generate a proof. Basically what you do is like you lay out the circuit of the program and then you generate a proof that the output of the circuit was 1, right? So it's like, because it's everything is laid out as as a circuit with like 2 input gates or a couple input gates and 1 or 2 output gates, depending on the type of or one or 2 input wires and 1 or 2 output wires, depending on the type of gate. And so, okay, so basically like you're basically like simulating hardware effectively. And so this is why you can't have an unbounded loop in, if you're laying out a circuit board, except of course, you have CPUs and like there's logic and you can manage memory and like using the von Neumann architecture, et cetera. You can do these things, right? So you can build a computer that of course is Turing complete because we're all using one right now, but in zero knowledge, you can't do it, right? Because you have to a priori know how the computation is going to halt because you have to prove that it did actually halt. Does that make sense? I hope I didn't like lose anybody there, but the bottom line is that this is not Turing complete. Now, you can, I guess I should maybe put a small asterisk there. You can simulate like basically the von Neumann architecture inside of a snark. And then you can you can effectively simulate the same like Turing completeness of a regular computer. This is called TinyRAM. For anyone interested in this research, it's quite fascinating. Basically they put, here, I'll show this right here. Let me find this. Okay, cool. This is a Medium article. I can't find the paper, but I think the paper's linked somewhere in here. Anyway, so TinyRAM is basically the idea where it's like, okay, implement a computer inside of a snark. As you can imagine, not very efficient. But those are the 2 things that are tricky, right? So you have to bound the length of the loops or bound the number of iterations in a loop. And then you can't have, like a typical computer, you would have like a heap and allocate memory to arrays, etc. You can't do that here, right? So you need to basically know a priori the size of everything, all the variables, etc. Helpful?
Yeah. So I was wondering, like, yeah, how expensive is it to deal with, like storage, right? So in EVM contracts, the storage, like abstracting that on the EVM case, like what are the difficulties that you would deal with because you have to like encode this
Storage in terms of like, so I
like
guess
like if you have a smart contract, right? Like that's interacting with storage to read write, representing that, like how expensive is that?
Yeah, so so this is the other interesting thing about this, right? So, okay, so this is maybe a good important point to linger also on some of the differences between Ethereum and Aleo. Actually, to make it simpler, I'm going to talk about the difference between Zexi and Ethereum. Aleo, we actually have a solution for this, but let me talk about Zexi. So storage in Zexi, like there is no on-chain storage model for contract state, basically, right? So the idea in Zexi was that all of the state for a program would exist off-chain. And if it was like a multiplayer, kind of like a smart contract equivalent, like Uniswap, for example, like you would need a sequencer that maintained the state that everyone was referencing when they generated their proofs. So they had data availability, which gets to your question earlier, Sergey. And then they also sequenced, okay, these transactions are touching the same state at the same time. I need to order them, right? Because to do, like in the model of Zexi, where everything is basically the UTXO model, like you can't have 2 people touching the same state at the same time. Now, this is solved in Ethereum, right? Because effectively all the nodes are sequencers, like, and they order transactions by, I don't know, the fee or the MEV, right? So this is in the traditional Zexi model, you don't have on-chain state associated with a program. Now in Aleo, this is something we're looking to implement, and we're trying to basically do a combination of the Ethereum and Zexi way, where you can have, and we actually, if you look at our docs, you'll see a reference to this. We have this concept of a finalized statement in Leo. So in Leo, you kind of have these 2 main blocks. It's your main program block, curly braces, and then you have finalized and then curly braces. And everything after the finalized statement is basically run in the same model of Ethereum, right? And so you can actually have programs with storage associated with them, and then the nodes basically process these, process the Aleo code compiled into AVM opcodes, and then they update that public state that's on chain. Now, what's the downside of that? Well, obviously the state then is not private, right? Like you can't have private state on chain there, and you can't have private logic because all of the nodes need to basically be able to see, okay, this is exactly the steps I need to get from A to B, just like Ethereum. Is that helpful?
I see. Interesting. Yeah, I was wondering, if there's like what would be the execution model? Interesting. So how do you like get composability then? Like if you want to interact with like state, or like they're just nowhere right now.
So
basically,
the only way to do composability is through basically the finalized statement. So I guess that's not true. So you can, one thing in this model that you can do is you can call programs inside of other programs, just like you import, it's like you import libraries and whatever your JavaScript project, right? And so you don't have to, so you can basically I say it like it's trivial because it is trivial for most languages, but of course in Solidity, right, we don't have that concept. You actually have to like copy and paste it. So it is kind of like novel from a blockchain perspective, but of course from like traditional programming languages or runtimes, it's like everyone does this, right? So you import libraries and they resolve and then it runs the logic of the library. But to your question, I think you're talking more about composability of like smart contracts effectively.
Yep.
Only way to do it in the traditional Zexy model, there's no way to do it. In our model, where we again basically try and take this part of Ethereum and we bolt it on. So basically, it's like you bolt on the Ethereum, kind of on top of this, the Ethereum model, the on-chain VM. That's how you would have to do composability, or you would have to run through a sequencer. And this is, by the way, true of every rollup, every ZK rollup out there, typically, right? Like this is usually composability is a very hard problem. And you need to basically have, see you, Sammy. You need to basically have a sequencer that manages in what order is state accessed and what place, and ensures that all of that happens in the correct order according to them, right? So this is, it's a tricky problem.
Alex, I guess on that though, can't you do two-step computation where first you have like a decentralized kind of ordering and sequencing followed by execution? Like, and you can still have like a decentralized network, right, that does the sequencing, and then execution just kind of follows that, so you don't introduce any assumptions.
Yeah, so you could, I think effectively like what you're kind of talking about is doing commit reveal kind of thing, right? So it's like, you basically, everyone like submits their intent to the network, hidden, and then the network comes to, agreement about, okay, hey, this is going to be the order of the transactions. And then the next block, they execute effectively, right? After all those are revealed. That's like one trivial way I could think of to do it. Yeah. But that's a different model than the thing is you still like it sounds simple, but it's complicated, right? Especially if you have contracts calling other contracts. Like think about a flash loan on Ethereum, right? Like the all the logic that goes into that, like all of these things, and you're touching a bunch of different state, different places. Like it's not trivial to engineer. And there's I think a lot of edge cases that come up that make it difficult. Guys, this was fun. Thanks a ton for having me. I've got to run to a meeting, but I hope you guys could follow it. I hope you learned something, and I hope it kind of got you interested in learning more about ZK. If you take nothing else away from this talk, I hope it's a little bit of interest to learn a little bit more about ZK. Of course, I'm biased. I hope you guys all want to learn more about Aleo, but in general, yes, I can share the deck. In general, I think ZK is really going to be a generation-defining technology that we'll see not only in Web 2 but in Web 3. So thank you very much for having me. Thanks for the invite. I hope you guys learned something. I will share these materials, and particularly the HackMD one, if you guys have comments or you want to see different stuff in there, I kind of made it to be like a living document. So please leave comments if you have any. And hope to see you all soon around the conference circuit.
Thanks so much, Alex.
Yep. All right, guys.